Hi, folks. Today we're going to learn about systems of linear inequalities. And just like systems of equations, here we're going to have one or more inequalities using the same variables. And we'll want to find a solution that works for every single inequality in the system. So, what does it mean to be a solution of a system of linear inequalities? It's just any ordered pair that is a solution to each inequality in the system. So and what this kind of means graphically is if we've got one inequality like this blue inequality here, and anything kind of above this blue dotted line is a solution to that blue inequality. And we've got this red inequality here, and anything on or below the line here is a solution to that inequality. If I want to have a solution to both inequalities, I need to be in this region here, where those two shaded regions overlap. So let's look at testing points to see if they are a solution to a system of linear inequalities. It's easy to see once we've got a graph where the solutions are, but what if we don't have a graph? How do we test a point? So if we are given an x coordinate and a y coordinate for a given ordered pair, then I can plug those values into each inequality in the system and see if I get a true statement or not. So if I plug in, let's see, if I do this equation and plug in 5 where y is and plug in 3 where x is, then I get the statement 5 is less than 6. Well, this is a true statement. So this ordered pair is certainly a solution to this inequality, but is it a solution to the whole system? We have to test the other equation to find out. So I will do, again, plug in 5 where the y is greater than or equal to x is 3. Okay. And now I see that it is true that 5 is greater than or equal to 4. This is a true statement. Therefore, yes, since I have all true statements, yes, 3 comma 5 is a solution to the system. All right. Let's look at another example. Here I have an x value of -2 and a y value of 0. So is it true to say that 0 is less than -4? That is a false statement. As soon as you get one false statement, you can actually stop checking. Once you get one false statement, this solution is automatically not a solution to the system. So we know now that this is not a solution. If we really wanted to, we could go ahead and check the other one because as we'll find out, this is actually a solution to the second inequality. 0 is greater than or equal to -2 plus 1. And it is true that 0 is greater than or equal to -1. But it doesn't matter. This is still not a solution. All right, let's look at graphing these problems now. How do we graph a system of inequalities? Really, this is the same process as graphing one inequality. You just have to do two or more inequalities on the same graph. So if I have y is less than or equal to 3, remember, if it helps you to think of this in slope-intercept format, y is less than or equal to 0x plus 3. That way it's really clear what the y-intercept is and what the slope is. So the y-intercept is up here at 3, and there's 0 slope, which means I have a straight horizontal line here, like this. And notice that I drew a solid line here. My solid line is because there is an equal sign in this inequality. That's that points on the line are part of the solution set. Points on the line are solutions to this inequality. Let's graph this other inequality here. Y is great. Oh, I'm sorry. I didn't actually finish I didn't finish with my shading. I talked about whether it's shaded or dotted. I'm sorry, a solid line or a dotted line. And now I have to talk about the shading. So y is less than or equal to 3. I want values of y that are small, less than that expression that I just graphed. So I want to shade down here. Now, unlike yesterday, I'm not going to just go ahead and shade in what the whole half of the piece of paper, because I'm about to graph another line on here, and the paper gets messy if you have lots and lots of shading. It's hard to fix things if you've made a mistake because there's a whole lot of erasing to do. So for right now, I'm just going to draw arrows to indicate where I'm shading. Here my y-intercept is 2, so I'll go there. And my slope is +1, so I'll draw some extra dots here. And this time I want my line to be dotted, so it's not going to be quite so tidy of a line because I'm trying to draw it dotted. So I can't use the draw straight line feature of my software here. And now I have graphed the equation or the inequality. I have thought about whether it should be a solid line or dotted line, and now I have to think about my shading. So in this case, I want y values that are bigger than the expression I just graphed. I want large values of y, which means I want to shade in the region that is above my dotted line. And if you look at the area where if you look at the regions where my red and purple arrows are both covering, that is the solution area. That's the region I want to shade. And so rather than shading a whole bunch of stuff red and a whole bunch of stuff purple, and then trying to figure out the zone where they overlapped, here I'm restricting my shading to just one zone of the graph. It just helps keep things a little bit tidier and easier to keep track of. So I could pick any point here on the in this shaded region and use it as a solution. So for instance, right here, the point -4, 0. I see that that is a solution, or I think it's a solution. It's in the shaded area, but I can plug those values into my equation and confirm that this is in fact a solution to the entire system, to every inequality in the system. So I've got 0 is less than or equal to 3. Yeah, that checks out. And now I have 0 is greater than -4 plus 2. 0 is greater than -2. Yes, that checks out. So I have confirmed that I've shaded the correct area of the system. Of course, we aren't always given equations in slope-intercept form. Sometimes we have to rearrange them ourselves. So if we subtract 2x from both sides of this equation, we end up with y is less than -1 minus 2x. And looking at the other equation, we can do something similar, subtracting 2x from both sides of the equation, and we get the inequality, and we get y is greater than 3 minus 2x. Okay. So let's graph each of those lines. Here I have a y-intercept of -1. So I'll plot that. And my slope is -2. So when your slope is -2, you can think of that as being -2 divided by 1, or you can think of that as being +2 divided by -1. So I can either go down to right 1, down to right 1, or I can go up to left 1, up to left 1, up to left 1. Now, based off of my inequality, this is going to be a dotted line. So let me draw a dotted line here. And with this dotted line, y is less than this expression. So I want to shade the region where the y values are small. I want to shade below the dotted line. Let's graph the red equation now. The y-intercept here is 3. Once again, my slope is -2, so I can think of that as going down to right 1, down to right 1, plotting a few more points here, or I can go up to left 1. Once again, this is a dotted line because my inequality does not have an equals sign in it. It is just a greater than sign. So I'm drawing my dotted line, and I want to shade in the region where y values are greater than this expression. I want my y values to get bigger and bigger and bigger, and my y values get bigger as I shade above this dotted line. So what we have here is a shaded region to the right, a shaded region to the left, and no overlap between the points. No overlap between the points. This system of inequalities has no solution because those shaded regions never overlap with one another. This will happen, for instance, when you have two inequalities with the same slope, but then shaded regions that don't end up overlapping with each other. Of course, if we can take equations and create a graph out of it, can we do the reverse? Can we take a graph and come up with the equations from it? So that's what we're going to practice next. We're going to think about the same thing, 3 things. What's the equation? What is it? And then converting it into an inequality by thinking about, did we shade above or below the line? And then is our line dotted or solid? And therefore, should there be an equal symbol as part of that inequality? So let's look at this example here. I'm going to refer to the purple line here, the diagonal, and I will also refer to the red line here, the horizontal line. So let's look at that purple line first. That purple line, if I were to write it as an equation, I would say y equals, and then I would try to come up with that mx plus b format based off of where the line is positioned. So I'm going to say y, and I'll worry about the inequality in just a moment. Let's see, my intercept here is at 0, and my slope, I go up 1, right 1, up 1, right 1. So if I do rise over run, that's 1 over 1. So my slope is 1. So I have 1x plus 0 as the expression that I'm relating to y. So now the question is, what inequality symbols should I put here? When I look at what's being shaded, I'm shading down from that line. I'm shading where the y values get small. I want the y to be smaller than the line. So I'm going to have a less than symbol here. Should it be a less than or equal to symbol? Well, because this is a dotted line, that means the line is not part of the solution for this inequality. So I do not include an equal sign. I just leave this as y is less than 1x plus 0. Now, of course, we can simplify that expression. 1x we can just write as x. We don't have to add the plus 0 because adding 0 does nothing to the expression. So we just have the inequality y is less than x. Looking at this red horizontal line now, again, we've got some y value that we want to kind of compare. We want to have our slope, and we want to have a y-intercept. What's our y-intercept? Our y-intercept is here at -2. And let's see, our slope, I don't rise at all when I have a run of 1 or a run of 2 or a run of 3. So my rise over run is 0 over any number. It can be 5, it doesn't matter. 0 divided by any number is in fact 0. So my slope here is 0. Now I'm going to think about that inequality symbol. Um, Here I'm shading values of y that are greater than uh, the line. So I want my y value to be greater than this expression that we just came up with, 0x minus 2. In this case, I do want to include an equal sign because this solid line is, uh, because the line is solid, any points that are on the line are included in the solution, and therefore the y value can be equal to this expression. Of course, once again, this can be simplified. We wouldn't write 0x normally. We would just say y is greater than or equal to negative 2. So this here is my system of inequalities corresponding to graph A. Looking at graph B, once again, I can kind of think of the red inequality and the purple inequality. Oops, purple. And so let's come up with equations for those. For my red inequality, I have gonna set this up in slope intercept form. Y mx plus b here. Um, in this case, I am shading above the line and my line is dotted. Therefore, I want values of y that are greater than whatever expression I'm about to come up with, and I do not want to include an equal sign there. The equation for the line, let's see, the y-intercept is at 1. And my slope, let's see, when I go from here up to here, that's a rise of 2 and a run of 3. A rise of 2 and a run of 3. So that's my coefficient for x. Y is greater than 2/3 x plus 1. If I look at my purple equation, this purple line here is a vertical line. This is not a function. Um, we can't write it in standard, uh, what's at least what's obviously appears to be slope intercept form, um, because the slope is actually undefined for a vertical line. Here, x just equals 3. Is that line. Of course, we're shading for smaller values of x here, smaller values of x. So we'll say that x is less than 3. And because the line is solid, if you're on the line, that is a solution. So we do include that equal sign. X is less than or equal to 3. Lastly, we have real world problems to look at. Because this absolutely does happen in business where you have multiple factors you're trying to optimize for shipping or whatever. And that this example is a shipping example. A company loads recliners and sofas onto a trailer. A recliner takes up about 40 cubic feet. A sofa takes up about 80 cubic feet. The trailer has a volume of 3,800 cubic feet. A shipment must have at least 30 recliners, and it must have more than 25 sofas. Write a system that represents the situation. Alrighty, so let's see what we have here. First, we want to take care, kind of define our variables. So I'm going to have my recliner, the number of recliners be my x value, and I'm going to have the number of sofas be my y value. And if so, I can come up with an equation. Uh, it's like I have a different rate for each of those items. So kind of standard form would be a good format for my inequality. I want to write an inequality that captures this idea that if I have 40 cubic feet per recliner plus 80 cubic feet per sofa, I'm going to take up some volume of space, but that needs to be less than or equal to 3,800 cubic feet. If it equals exactly 3,800 cubic feet, then my trailer is just perfectly, completely 100% packed full, which is possible. Perhaps not very likely, but it is possible. Um, uh, and this would be inequality number one in our system. Let's read the next bit of sentence. Um, the shipment must have at least 30 recliners. Okay, so recliners are my X value. I'm saying that my X value must be at the very least 30. X can be greater than 30, X can be equal to 30, but it can't be less than 30. Then we have a constraint associated with our sofas as well. We have to have more than 25 sofas. So sofas are my Y value. So my Y value has to be greater than 25. It cannot be equal to 25. It must be greater than 25. So I now have a system of equations, I'm sorry, a system of inequalities that describes this entire situation. So let's graph what we have here and see what our solution perhaps looks like. So, before I can graph this, I need to have kind of convert my purple equation here into a more easily graphable form, a slope-intercept format. So I'm going to get y all by itself on one side of the inequality. So I'm going to subtract 40x from both sides of the equation. And that gives me 80y is less than or equal to 3,800 minus 40x. And now I'm going to divide by 80, And when you divide by 80, you remember to do the distributive property. You have to divide each term in the addition subtraction problem by 80. So when you do that, you get 47.5 as your y-intercept, and your slope is negative 0.5x. All right, so let's graph that. Our y-intercept is 47.5 here, and we go down half of a unit each time we go to the right 1 unit. Graphing in that sort of small quantities on this graph, which has large numbers, doesn't really work well. So I'm going to think of my slope in a larger scale, not just down 1, right 2, but instead maybe something a little more manageable, like down 5, right 10. Kind of going by 5s and 10s makes more sense the way I've labeled this these axes. So if I go down 5, I go right 10, down 5, right 10, down 5, right 10. Okay, so that's what my slope looks like. And this does have an equal sign as part of the inequality, so I can draw a solid line here. And my values must be less than, y is less than this expression. So I want to shade the region where the y values are less than the line, below the line. Next up, I'm going to graph y is greater than or equal to 30. The 30 mark on the x-axis is right here. So if I go ahead and draw this line in, and there is an equal sign in this inequality, so I have drawn a solid line here. I want x values that are greater than this 30 value. So I want to shade x values here in this direction. And in fact, I already know I'm not going to shade anything up here, so I'm just going to get rid of that extra arrow because I know for sure I'm down in this region here. And now I want to graph my green inequality where y is greater than 25. Well, here's my y equals 25. So if I'm drawing a dotted line here, I want y values that are greater than that dotted line. So I'm going to shade up here. So you can see that blue, I'm shading to the right. Purple, I'm shading downward, and green, I'm shading upward. So all together, I'm shading in this tiny triangle region here. Now, any value in this shaded region, including on the blue line or on the purple line, that will be a valid solution to this system of inequalities. So if I just pick the point 35, 28. Let me just draw that in here in gray or in black. Uh, 35, 28 would be a valid solution. And what does this mean in the context of the problem? Remember, X value is recliners, so I can have 35 recliners. And for my Y value, I could have 28 sofas. And that would be a solution to the system. I hope this helped.